So now we are going to talk about this resampling methods, and this is not totally new because in some parts of the lectures that we have covered before, in the classification and also the linear regressions, we have actually done some part of this. So let us just talk about what does it mean? Okay, what is a resampling methods? Okay, so the goose is already make sounds now. Okay, so the resampling methods involve repeatedly drawing samples from a training set and then refitting the model of interest on each sample to obtain additional information about the fitted model. Okay, so what we have here is we use these training data sets in order for us to build a model. And what we do is we resample this training set again and again and again, and each time we refit the model. So we're not, fitting, and now we use the word refitting, resampling and refitting. So we refit the model again and again and again on each of the sample that we make in order for us to obtain additional information about the fitted model. So we're not just like we have one training set and then we just build one model and we're happy with it. Okay, so in the resampling methods, we resample and refit the model of interest again and again. Um, I would say that previous decades ago, this technique would be computational expensive because let's say you have a large data set and you want to resample again and you want to refit the model again. So this is going to be really computationally expensive. It will take time and will be costly because you will involve fitting the same statistical method many times using different subsets of the training data. However, due to the recent advances in the computing power, so the computational requirements of resampling methods generally are not prohibitive. Okay, so what are the most commonly used resampling methods? Here we have cross-validation and the bootstrap. But in this class, we are going to talk only on the cross-validation because the bootstrap is, it is quite advanced and you can use it. If you are interested, you can read it in the textbook. Okay, so the cross-validation can be used in two ways. One for model assessment, in which you try to estimate the test error, which is associated with given statistical learning methods. And you use this in order to evaluate the performance of the fitted model. And the cross-validation can also be used for model selection, in which you use this cross-validation to select what is the appropriate level of flexibility. So flexibility is whether the model is flexible or the model is complicated. So what is the optimal number of flexibility that you will allow that will reduce the test error. And the bootstrap is used in several contexts, but most commonly it is used to model selections to provide a measure of accuracy of a parameter estimate or of a given statistical learning methods. But we are not going to cover this bootstrap in this class. Okay, now I want to talk about model flexibility or model complexity and its relation with the prediction error and how we're going to, find what is the optimal level of model complexity when we look at the training error rate versus the testing error rate. So you build the model based on the training data sets. So when you increase the model complexity, what happened is that the prediction error for the training sample, which is the blue line here, will decrease because the more complex the model, you can try to fit as much data sets, data point as possible. So what you will end up with is a very complex model where you try to fit each and every data points that you have. So if you have a very high model complexity, the prediction error or the error rate for your training sample will reduce. However, if you try to use this model, which is fitted on the training data sets, and you try to fit and you try to fit this model into a testing sample, which is a new data, okay, at first it will go down, the error will go down, but as the model complexity increases, you can see that the prediction error is also increased. So when we want to fit a model, when we want to find the suitable model, we always have this in mind, okay? The more complex the model is, you will prone to have overfitting, where it can fit the training data very well, but it's going to perform very poor on the new data. So if you want to use your model for prediction, what you want is a model that is flexible enough that it can reduce the prediction error rate for both the training and also the testing sample set, the training sample. And you want to have an optimal level of model complexity in that case. Okay, now we want to talk about this cross-validation, but first I just want to check about this, if it is going on, right? Okay, so the test error is the average that results from using a statistical learning methods to predict the response on a new observation. So this test error is taken from, you fit the model on the training data set, and then you try to predict what would be the value of the testing data sets, and from there you compute the test error. Okay. The test error can be easily calculated if a designated test set is available. However, unfortunately, this is not usually the case, okay? Because sometimes you do not have very large data sets and you have to use all of your data for, for the training data set, or to use it to build the model. And okay, so the training error can be easily calculated by applying the statistical learning methods to the observation used in its training. So the training error rate often is quite different from the test error rate, and in particular, the former can dramatically underestimate the latter. Why? Because we fit the model based on the training data sets. So if you have like a certain level of the error rate for this training data sets, it doesn't tell a real picture about what is going to happen with the testing data sets, because you build the model using the training data sets. Yeah. So in the absence of a very large designated test set that can be used to directly estimate the test error rate, a number of techniques can be used to estimate this quantity using the available training data. So what it means here is that even if we do not have a test data sets, in which, in the previous lectures, we divide the data into two, one is training and one is testing data set. That is just for, exercises. But in the case where it is impossible, or where you cannot get the test data sets, there are a number of techniques that you can use to estimate the quantity using the available training data. The question is how? So in this lecture, we will consider several class of methods that estimates the test error rate. Okay, what we do is we'll hold out a subset of the training observations from the fitting process, and then we're going to apply the statistical learning methods or the statistical model to those held out observations. Okay, so in this class, we are going to cover three methods. So the first one is the validation set approach, and the second one is the leave one out cross validation, LOOCV, and the third one is the k-fold cross validation. And towards the end of this lecture, also we are going to discuss the bias variance rate for k-fold cross validation, and also the cross validation on classification problems. So let us go to the first one, which is the validation set approach. So in the validation set approach, this might seem familiar because we have done this before in the previous lectures. What we do is we randomly divide the data sets, the available sets of observations, into two parts, which is the first part is the training data sets, and the second one is the validation data sets. So we call this validation data set as the holdout set. Okay, so what we do is first we fit the model on the training data sets, and then the fitted model is used to predict the responses of the observations in the validation data sets. Okay, and this resulting validation set error rate, for example, like we use MSE, will provide the estimate of the test error rate. Okay, so what we do here is we fit the model on the training data sets and we predict what would be the response variable in the validation data sets, and then we compute the MSE, where the MSE is actually the difference between the actual value and the predicted value. And this this MSE, which we obtain from the validation data sets, actually provide the estimate of our test error rate. So let us look at this example. For this one, we use the validation set approach on the auto data set. And here we want to estimate the test error rates that results from predicting the MPG. So if you have R, and you can get this auto data set on R, and this is what we're going to do later in the lab session. So what we do is we try to predict the MPG using the other predictors, and we use polynomial functions of horsepower. Okay, so the predictor here is the horsepower. So on the left graph here, what you see is the validation error estimates for a single split into training and validation data sets. Okay, so this is for the single split, which means that you might divide your data into how many percent for training data sets, how many percent for the validation data sets. And what you do is, in the first dot is when you have y is equal to, where y is MPG, y is equal to beta naught plus beta 1 horsepower. Okay, and in the second dot here, you have y is equal to beta naught plus beta 1 horsepower plus beta 2 horsepower to the power of 2. And then you're going to increase the model complexity until you have up to the horsepower to the power of, horsepower to the power of 10. All right. So here you increase the model complexity. So basically, how many models you have here? You have 10 models. Okay. So in the first model where you have y equal to beta naught plus beta 1 horsepower, this is the MSE, which is 23 point something. And then if you add the model complexity by one step here, you have up to horsepower, you have up to horsepower squared. So you can see that the MSE has reduced a lot, and it actually increased a little bit when you increase the model complexity and it goes down. Okay, but basically you can see a huge decrease from the first to the second model here. Okay, so this is based on a single split of the training and validation data sets. So on the right hand side, what you do is, instead of having a single split, okay, for example, like maybe one person divide the data into 20% validation and 80% training, and the other person use slightly different, okay, or they use the same 20 and 80, but they sample, they get the different sample. So this is the resulting output. Okay, so you can see you run it for many times, where you repeat 10 times in this case, and each time use different random split for the observation into training and validation data sets. And again, you can see that here from the first to the second degree of polynomial, it has decreased a lot, even though you can see that some of it has decreased even further, like the yellow here. When you arrive at degree of polynomial equal to 7, it has decreased a lot, but you can see that the big decrease is actually when the degree of polynomial is equal to 2. Okay, so that is the validation technique, okay, the validation set approach. And now we're going to talk about the leave one out cross validation. Okay, so the LOOCV involves splitting the set of observation into two parts. Again, if you just read on the first sentence here, this sounds like similar to the previous method, which is the validation set approach also split the data into two parts. The first part is the training, the second part is the validation. Okay. However, the LOOCV, okay, instead of creating two subsets of comparable size, in LOOCV, we leave out a single observation. Okay, each time we leave out a single observation x and also y, its corresponding y. So if you have more than one predictor, you can have x1, x2, x3, and so on. Okay, but you leave out one observation where this one observation is used for the validation data sets, and the rest of the data will be the training data sets. Okay, and then what you do is, for example, like you have, I think, yeah, we have a picture here. So in the first step, you leave out the first observation, and which is on in the orange here, and you fit the model using the blue part here, and you compute the MSE for the first one. Okay, and then the second one, you take the second observation out, and you fit the model on the rest or the remaining of the observation, and you try to use this fitted model to predict what would be the value of the response for the second observation. And then you compute the MSE. And then you remove, in the third step, you take the second observation back into the sample and you remove the third observation. And you repeat this n times. Okay? And for each of this, you compute finally the cross-validation value is computed by taking the average of all the of all the mean squared error that you have here, which is the difference between the actual and the predicted value of each of the held out observations that you have. So this is LOOCV. Okay, so each step you're going to remove one observation, fit the model into the rest of the observations, and try to predict what would be the response for that observation that you have already removed. Okay, so since, for example, in the first step, the first observation, which is x1 and y1, since this is not used in the fitting process, so MSE of the first one is given by the actual minus y hat, where y hat is the predicted value, and this is squared. Okay, so MSE is given by the actual minus the predicted squared, and this value provides an approximately unbiased estimate for the test error. Okay, but even though MSE1 is unbiased for the test error, this is a poor estimate because it is highly variable since it is based upon a single observation. Okay, and so what we do here is that we repeat the procedure n times. So if you have n equal to 50, we will repeat it 50 times to produce n squared errors, and finally you compute the average. Okay, so what is the advantage of the LOOCV over the validation set approach? Okay, so LOOCV has far less bias, thus it tends not to overestimate the test error rate. Okay, because it is less biased, because why? You leave out one observation each time, and you leave out each of the observations that you have, instead of, you divide into 30% here and 70% there, and if you change the sample, the number of observation, or you change the components, it's going to be different results. But this one, it has far less bias because everyone is doing the same thing. Everyone is leaving the first observation the first time, and then the second time you leave out the second observation. So everything is calculated into the calculation. Also, in contrast to the validation approach, which will yield different results when applied repeatedly due to randomness in the training and validation set splits, by performing LOOCV multiple times, it will yield the same results because there's no randomness in the training and validation set split. So this is what I tried to explain earlier. Okay. Okay, now we go to the third one, which is the k-fold cross-validation. So this k-fold cross-validation involves randomly divide the data into k groups or k folds of approximately equal size. So let's say if you have n equal to 100, so if you divide into 5 groups, so each group is going to have n equal to 20 observations. Okay, so the k-fold cross-validation is actually quite similar to the LOOCV, except that in LOOCV, each time you have to remove one observation, and you have to run and you have to refit and resample for n times. So if you have 100 data sets, you're going to run it for, if you have 100 observations, you're going to refit the model 100 times. But in the k-fold cross-validation, instead of using an individual observation, you group this observation into folds. Okay, so if you have a total observations of 100 and you divide into 5 folds, okay, so you just have to run it 5 times. Okay, and each time you're going to remove one group from from the calculation. So the first fold is treated as the validation data sets, and then the model is fit on the remaining k minus 1 folds. And then we're going to compute MSE the same way as how we compute it in the previous technique also. So MSE is then computed on the observations in the held out fold, and this procedure is repeated k times. So if you divide into 5 folds, you're going to repeat 5 times instead of repeating it for 100 times. And then this process will result in k estimates of the test error, which is MSE1, MSE2 until MSEk. And this, the k-fold CV estimate is computed by averaging these values. Again, this is very similar to the LOOCV, except that instead of having 1 over k, instead of having 1 over n, here you have 1 over k. So you're averaging based on the number of groups that you have. Okay, basically the k-fold cross-validation is widely used approach for estimating the test error. And the idea is to randomly divide the data into k equal size parts. And we leave out the part k, okay, one part, and we fit the model to the remaining k minus 1 parts. And then we obtain the predictions for the left out k part. And this is in turn done for each of the parts, the remaining parts, and then the results are combined. So this is how it looks like. Let's say you have k is equal to 5 here. So you divide your data into 5. And the first step is you use the first group as the validation, and the remaining is used as the training data set in combination. Okay, so in combination, you're going to use part 2, 3, 4, and 5 to fit the model. And you try to predict what would be the response variable for this validation data sets. And from here, you compare the actual value and the predicted value, going to get the MSE for the first part. And then you're going to repeat for the second part until the last. Okay. So, so this is actually the same as in the previous slides. So I'm just going to skip this one. So actually LOOCV, you can see a very high similarity between these two techniques. And LOOCV is actually a special case of the k-fold CV. And the advantage is the advantage of the k-fold CV is actually it is less computationally expensive. What I mean here is that instead of using k is equal to n, which is instead of leaving out each one of the observations that you have, now you group them into 5 or 10 group or any number of groups, so you do not have to run the model as much as you would have run them using the LOOCV technique. Okay, now is we're going to discuss about the biased variance trade-off for the k-fold CV. So basically LOOCV give unbiased estimates of the test error, because each training set contains n-1 observation, and you refit the model almost as many as n. Okay, what I mean here is that each training set contains n-1 observation, okay, which is almost as many as n, almost as many as the total number of observations that you have. So basically it gives the unbiased estimates of the test error. And the k-fold CV leads to an intermediate bias because instead of looking at instead of removing one observation per steps, okay, you have a group here. So if you look at the bias here, of course you would prefer the LOOC, okay, because it is the unbiased estimate of the test error rate. However, if we try to look at the variance, okay, bias is not the only source of problem. Bias is not the only source of concerns. We also need to look at the variance. So we would say that LOOC has a higher variance. Because of why? Because averaging outputs from n-fitted models, each trained on almost identical observations. So the output are highly positively correlated with each other. Okay. In the first step, let's say you remove the first observation. So you have like observation 5, 6, and 7 in the observation. In the second one also, when you remove the second observation, we still have the same observation 5, 6, and 7. So they are actually very highly correlated with each other. So that is why the LOCV has a higher variance compared to the K-fold CV. The k-fold CV has a lower variance because it averages the outputs from k-fitted models that are less correlated with each other. Okay, so in saying that whether the LOOCV is always better than k-fold CV or the other way around, we really can't be sure. Okay. All right. So all that we have talked just now is the cross-validation technique for when the response variable is numerical. What about when the response variable is classification? Okay, you have classification tree or the logistic regression. So instead of using MSE, we now use the number of misclassified observations. So if you look at this one, the formula is almost the same as the MSE, except that instead of getting the actual value minus the predicted value, now we have the error here, which is the error is when the actual value is not similar to the predicted value. So let's say you predict it to be 1 and the actual is 0. So this is not equal, so it will become 1. Okay. So in total, we're going to have the average of the misclassified observation or the misclassification rate. Okay, lastly is just an example. So here what we have is, this is the example for the classification problem. So here, if you look at the first picture, we have a two-dimensional classification data in which the purple dashed line here is actually the Bayes decision boundary. And you can see you have two classes here. You have the blue and you have the orange one. And if you look at the Bayes decision boundary, it works quite well to divide the blue into into one part and the orange into the other part, except that there are some of the observation which is misclassified by the Bayes decision boundary. But in overall, we would say that the Bayes decision boundary is working quite well in these data sets. Okay, so what we do is because this is a simulated data, so basically we would know what is the true test error rate because we are the one who generated these data sets. Okay, so what we do is we try to fit this using logistic regression. So in the first picture here on the top left, you can see this is the logistic regression for the linear, okay, where you have up to the power of 1. So the degree is equal to 1 here. And the test error rate for this is given by 0.201. So the logistic regression is given by the black solid line here. And you can see that it is very, very flexible and it is not able to actually capture the boundaries really well. There's a lot of errors here. So no wonder that the test error rate is actually very high, 0.2 compared to the others. So this is the logistic regressions to the power of 2, and you can see it is quite curvy, but still it can't really capture the boundary between the orange and the blue. And we increased up to the power of 3 here, and you can see that it's working much better than the previous two. And this is a more flexible model with the degree of 4 here. Okay, so when we try to get the test error rates for the linear, we have 0.2, which is the highest. And for the quadratic, we have 0.197. And when we have the power of 3, we have 0.16, which is the lowest of them all. And as you increase the model complexity, is actually the test error rate actually increased a little bit to 0.162. Okay, and because this is a simulated data, so actually we are able to know what is the true error rate. So the true error rate is given by 0.133 here. Okay, so this is the error rate which is obtained from the Bayes decision boundary, which is 0.133, much lower than all the 4 models that we have here. Okay, so in practice for real data, the Bayes decision boundary and the test error rates are unknown, but because this is a simulated data, so that's why we are able to compute them. So how might we decide between the 4 logistic regression model displayed here? So we can actually use the test error rate. And from here, you would say that, okay, the third one here works the best because it has the lowest error rates. Okay, so this is, all right. This is the error rate, and this is the order of polynomials used. And the black line here is actually the 10-fold CV error rates by fitting the 10 logistic regressions. And again, if you look at the horizontal axis here, so this is the order of polynomials used from the power of 1 up to the power of 10. And you can see that the CV error rates actually reduce very much, and it arrives at the minimum when the order of polynomials is equal to 4 here. Okay, and the brown one is actually the true test error rate, and you can see that the true test error rate is actually when the order of polynomial is equal to 3, and the blue line here is actually the training error rate. So again, if you look at the training error rate, as you increase the model complexity, the error rate for the training data set will continuously reduce, okay, because you try to fit the data as much as possible on the training data sets. However, it won't perform similarly good if you try to fit the same model to the testing error rate. So that's why the black line here, you see that as you increase the model complexity, the line goes up, okay, the error rate goes up. So if you look at this one, the minimized or the minimum of the CV error rates from the 10-fold methods is actually quite similar to the true test errors. So we will say that it will give us quite a good approximation of what would be the true minimum test errors. Okay, actually in the beginning I was thinking of including the KNN approach. However, because we no longer include the KNN approach in our syllabus, so you might just want to leave this part out. Okay, so that is the end of this lecture, and we will continue with the lab session. So in this lab session, we are going to go through several cross-validation techniques. And the first one is the validation set approach. And for this one, because we will be using auto data from the library ISLR, so first is I have to load this library into R. And then because the next step that we're going to do is we're going to use the sample function. And this sample function is based on randomness. So let us use the set seed so that we want to make sure that our results are replicable and everyone will have the same results. Okay, so we use set seed of 1, and the next one is we use the sample function. So this sample function is what you have here. You can just run question mark sample, and on the help function here on the bottom right, you can see that the sample function take on sample of the specified size. And the syntax is want to make a sample of X, and this is the size that we want to have. Okay, so basically out of 392 observations, we want to make a sample of 196 observation. So the number that we're going to have in the train, in this data, in this vector train, is the number from 1 to 392, where there are 196 numbers. So you can just type in head of train just to see what are the first few observations, and you can see that the numbers here is actually between 0 until 392. Okay. So the next is we're going to use the LM function, and because this one we want to fit the linear models on the MPG, and the predictor is horsepower, and the data here is from the auto data sets. And here we want to use subsets equal to the training data sets. So we're just going to, just going to run this model on the training data sets. And it is good to know what is the dimension of the training data sets. Oh, sorry, the length of the train. All right. We have 196 observations in the training data sets. So this 196 observations is the one that we use to fit these linear models, and we save all the outputs into lm.fit. Okay, so now next is I'm just going to attach the auto, and I'm going to run this. Okay, so this is what it means here is that this is the mean of the MPG, which is the actual value of the MPG, minus the predicted value of the MPG if we try to predict this auto data sets using the lm.fit, using the linear model that we run just now. Okay, and here we have in the square bracket here is that we do not want to run this on all the observations in the auto data sets. Instead, we just want to run this on the testing data sets. And we know that the testing data sets is the complementary of the training data sets. So that is why we put the negative here. Okay. So if you have 100 observation and 70 is used for training, so this negative train is the 30 which is left as the validation data sets. So this is not, minus means this is not the training data. Okay, so what you have here is the actual value of y minus y hat. So this bunch, the predicted value is actually the y hat. So y minus y hat, and we have squared, and this is just based on the validation data sets. Okay, and the average is given by 23.26. And then next is we're going to run the other model, and this one is we have the linear model of the MPG, and here on the predictors we use the poly function. Okay, so where the poly function is actually the polynomial function. So it is good if we can just run here poly. Okay, so this is the polynomial function. You can put up to how many degrees of the polynomial that you want to have. So if you put the poly of horsepower, comma 2, so this means that instead of having, you have y is equal to beta naught plus beta 1x. So this is a 1 degree. Okay. And then you have y is equal to beta naught plus beta 1x plus beta 2x to the power of 2. So in this case, this is a 2 degree. Okay, so this is also called as quadratic. And you can just add it. Okay, y is equal to beta naught plus beta 1x plus beta 2x to the power of 2 plus beta 3x to the power of 3. So this is already 3 degree or cubical model, right? So we try to fit many models here. The first one is the linear, which is this one. And the second one, the second degree and the third degree. And we're going to see what would be the MSE. So, okay. So, oops. So the mean, the MSE between the actual value minus the predicted value based on this LMN fit, LM fit 2 is given by 18. So we can see that MSE is already decreased for the quadratic model compared to the linear model here, okay, which is good. Remember that we always want to have the minimum MSE. Yeah. So now we just try to further increase the model complexity. Now we include the cubical model where we have polynomial of horsepower, 3, and we're going to compute the MSE for this one. It is 18.79, which is slightly increased from the second model, but it is not so much different. So if you want to compare between the MSE, between the linear, quadratic, and the cubical model, I would say that you would prefer the quadratic model because it gives you the minimized error. Okay. All right, so next is I'm going to show you another exercise here. Okay, and for this one, just bear with me for a while. For this one, let's just use set.sit of 2. So if you want to ask me why we use number 2 instead of all other numbers, so it is totally up to you, okay? Because we want to have this result, replicable whenever we want to run it. So we just use the same set, and we don't care about the numbers that we put inside here, okay? So let's say we still have okay, let me see. So this whole bunch is actually I just realized that this whole bunch is actually the same code as we do in the above. So I'm really not sure. The only difference is that the set.sit is equal to 2 instead of set.sit is equal to 1 here. So I think I'm just going to skip this part, okay? Because basically it is just the same thing, okay? So this whole bunch is actually the same as the bunch in the above, except that we use the different set.sit here, right? So there must be a mistake when I write this code. Okay, so that is the validation set approach, in which I'm going to explain again. What we did was we used this sample function to divide our data into two parts. The first part is the training, the second part is the validation. And here we have 196 observation out of the total of 392 as the training data sets, and the remaining is the validation data sets. And then we refit different models and we compute the MSE, and we basically choose the lowest MSE. Okay. Now we want to talk about the leave on out cross validation, the LOOCV. So first is I just want to show you that we're going to use this cv.glm function, okay, and this cv.glm function comes from the package boot. So you have to install this package first. So to install the package is just install packages and then boot, right? Because I've already have this in my computer, so I don't have to install it again. And after you install .packages, you have to run the library of boots here, okay? And what I want to say here is that because we want to use this cv.glm function, and this cv.glm function only works if you run the model using glm function, okay? Unfortunately, it won't work on the lm function here. So because of that, so we will use the glm function, but I just want to show you one thing. Let's say you want to run this one, okay? So this is the linear model function, the lm function of mpg on horsepower using the data equal to auto, and you save this on lm.fit, and we just want to see what is the coefficients of this lm.fit. So this is the coefficients. So what if we use the glm function? We get the same results, okay? So here we use the glm function on mpg on horsepower using the data auto, and we store this in glm.fit. And when we call out the coefficients, we see that the answers is exactly identical, okay? So basically, if you want to run the linear model, you can use the glm function, the GLM function here. So GLM function can be used for various models, including linear models. And if you remember last time, you also used this GLM function for the classification analysis, which is logistic regression. But for the logistic regression, you have to put family equal to binomial here. Okay, so if you do not have family equal to binomial, it will treat it as a linear model. Okay, so let us do this LOOC. First is you have to install the package boot, and then you have to call the library. You have to load the library into R by using the library function. And first is I'm going to use the GLM function to fit the linear model on MPG. The response variable is MPG, and the predictor is horsepower. And we're going to save this in glm.fit. And then we're going to use the cv.glm function to to compute the leave one out cross validation. So this is cv.glm on auto, comma glm.fit. So this is based on the glm.fit here, and we're going to store this in what we call as the cv.err, cv errors. Okay, so let me just quickly run this one, cv.glm. Okay, so this is the cross validation for the generalized linear model. So you can actually read read more on this one. It is also can be used for for the k cross validation, k-fold cross validation technique if you introduce the value of k here. All right, so next is we're going to call out the results or the output. So you type in cv.err $delta, where delta is one of the output that we store in cv.err. And what we see here is 24.23, and this is 24.23. So basically this is the MSE. And it has two values, and you can see that the values here is actually identical, but this is not always the case. So the identical values here means that the first one is the MSE, and the second one is the MSE, which is corrected for the bias. But in this case, because you just run it for one time, so you only have like two identical values. Okay, now what we want to do next is in this whole bunch, I'm going to explain about this. Okay, let me explain about this first. Okay, in this bunch here is we're going to use the loop function. Okay, so this for is actually the loop function. Okay, so the for here is the loop function. And what it means here is that, okay, what we want to do is we want to run this GLM function many times. In fact, we want to run it for 5 times. And each time using the power of 1, and then the second time is to the power of 2, and to the power of 3, and so on. Okay, so what we're trying to do is we're going to use this GLM function to fit MPG on horsepower, but we're going to use the polynomial function, where we start with the power is equal to I, where the first time I will be equal to 1, and the second time is I will equal to 2, 3, 4, and finally 5. Because here you have for I in 1 until 5. So we're going to run this 5 times. Each time I will correspond to the number from 1 to 5. So we're going to have the model, which is from the 1st degree to the 5th degree. And then for each of this model, we're going to compute the cv.error here, which is using the function cv.glm. Oops, I've just check here. Okay, we're going to use the cv.glm. So each time we fit the GLM model here, the next line is we will compute the cv.glm based on the auto data and based on the glm.fit, which is the model that we fit in the first line here. Okay, and we want to have the delta with the dimension of 1, because as you can see previously, the delta will give you two results. One is the MSE, and the other one is the MSE corrected for the bias. But in this case, we are only interested in looking at the MSE. All right. So in the end, this CV dot error, we're going to have 5 value for this CV and error based on the value of I. So I equal to 1 corresponds to the power of 1, I equal to 2 corresponds to the second power, and so on. So we're going to have 5 total value for the CV dot error. But in R, technically, you can't have CV dot error by its own. So what I mean here is that if you want to have the CV dot error in here, you need to introduce the CV dot error first. So it's like you want to fill this CV dot error with a certain value. First, you have to introduce it first. Okay, so we just introduce the vector here. So we just run cv.error, which is using the rep function, the repetitive. So we're going to repeat 0 5 times. So this is when the data manipulation part comes into play. Yeah. So that is why in the very first part of the lecture, we actually play a lot with R, because this will be helpful in the coming lectures when you want to do some data manipulation technique. So if we didn't cover that one, then it's going to be quite difficult for you to use R actually. Okay, so let us just type in cv.error. So you see here the 0 is repeated 5 times. Okay, so we're just going to run this loop function, right? Just going to check if this is working, right? So here we have already run it, and we can just type in cv.error. So this will take a few minutes for the output to come out, because you ask R to fit this model 5 times and compute the cv.jlm. So this is actually taking quite some time to do. Okay, so here is the value of the cv.error. So the first one corresponds to when you have the linear model, and the second one is when you have the quadratic model, and this is the third one where the degree of polynomial is equal to 3, and this is 4, and this is 5. Okay, so if you want to know, you can already know what is the minimum value here, but if you just want to know cv.error here, so the cv.error is minimized at the power equal to 5 here. Okay, so this is the minimum one. Okay, and then next is, okay, what we mean here is that if you want to do a model evaluation, you would say that based on this cross-validation technique, the model that have the minimum error rates for the testing data sets is actually the model with the power of 5. Okay. Now we want to go to the k-fold cross-validation. And for this one, let us just use set seed equal to 17. So I'm going to remove that. So we're going to run this again, set seed of 17. And for this one, we're going to introduce one vector, which is cv.error.10. So this is just a name, because we just want to give some indication that we're going to use 10-fold cross-validation. So this is actually repeat 0 10 times. So if you type in cv.error.10, you're going to have 0 10 times. And next is we're going to use the loop function, and this time, okay, we're going to use the GLM function. First is we fit this using the GLM functions of MPG on horsepower, and exactly the same as before, but instead of using 1 to 5 here, we have 1 to 10. Okay. And cv.error.10 is given by cv.glm. All right. Here, the difference between this one and the previous one is that now we have k equal to 10. Because we want to use this cv.glm for the k-fold cross-validation. So you have to introduce the value of k that you have here. Otherwise, if you didn't put k, so it will think that this is a LOOCV technique. Okay, so I'm just going to run this loop function, and finally we just want to find this cv.error.10, and let us look at the minimum of cv.error.10. So the minimum is here, which is 18.87. Okay, and it will be useful also if you can use cbind of 1 to 10 and cv.error.10. So you can see here the minimum test error is at here, okay, when the degree of polynomial is equal to 9. Okay, so if you want to gain more understanding about this technique, there's an exercise given to you on the lecture on spectrum, and also you can read the books. There are a lot more exercises. You can try to do the exercises to gain more understanding of this one, and I believe that some of this technique is also covered in other lectures as well. So you can do the exercises, and if you have any question, you can post on the Q&A link, and we can have a discussion on this one. Okay, so that's all for